SEP College Engineering India. Welcome to the Honorable Miss Shalini. Yeah, as an assistant professor. I'm sorry. Yeah, welcome to the Honorable Miss Shalini as an assistant professor, Department of Computer Science and Engineering. And for the topic today is fundamental of computer system architecture. And for today's session is being live streamed on the University of STEKOM YouTube channel. And now I will read our agenda this afternoon. First, we will start class presentation delivered by Miss Salini and continue with the Q&A session. In the next session, we have time for documentation unless time is closing. Okay, let's begin. We will start class presentation delivered by Miss Salini. The time is yours. Thank you.
Thank you, ma'am. Shall I stand up?
Yes, ma'am. Go ahead.
Okay, good morning, everybody. Okay, I'm going to teach about fundamentals of computer architecture. It is a base and a base of our computer system. We all know what is computer. A computer is an electronic device that is used to process, stores, and execute the instructions to perform tasks. So for that, how we are going to explain, I'm going to explain how it is going to execute everything, how it is going to process one by one instructions. You are speaking in English, how that computer is going to understand that English. It is whatever we are speaking is a high level language. The system only understand low level languages. How that high level language is going to convert into low level language? What are the components used to convert this high level language into low level languages? And what are the constraints keeping the performance low? These things we are going to see here. So first, we will see what are the components inside the computer. Um, we will be having central processing unit, memory, storage, that is secondary memory, input devices, output devices, and peripherals. These things, these basic things we all know already. Okay. Next, we will move on to the what is the evolution of computer. First, initially, what it have arrived and how now we are. Okay. Initially, um, we had only the single core processors. That is, only one multiprocessor system will be there. So it will perform only one instruction at a time. In 1950s, later it is get developed into multi-core architecture. That is, in a single processor, we are having the capacity to execute more than one instructions, that is parallel instructions. It leads to the parallel era. That is, in 1990s we started to develop the parallel processing systems. Okay, we all know our server will be in any other locations, so we are browsing the more than millions of people are going to browse at a time from all over the world. Okay, how these are going to be done parallelly using these architectures, the architecture development, we are making it possible. Okay, in 1990s we started the parallel processing. Okay, in 2000s there is some rise of multi-core architectures. That is, it is going to it is going to perform a complex applications. Okay, in 2010s we have started to derive the mainframes, high performance computing and all. We have started to develop, that is becoming mainframes or mainstreams or cloud computings. These and all get developed in 2010. So cloud for cloud computing, or nowadays we need a parallel processing and multi-core systems in general for even to do a day-to-day life. Okay, these are the generations of computer architecture. So in first generation, that is from 1940 to 50s, they have developed the vacuum tubes where the data will be it occupies a single room, whole rooms, and it is large, slow, and the power and heat is emitted is more here. Okay. In 1945, the von Neumann described the architecture that computer will have only the five functional units, that is central processor units, input unit, output unit, memory storage, and control units. Okay, so he only designed this functional units. So now on nowadays we are using that type of units. And in second generation from vacuum tube, they have transmitted to the transmitter. Okay, so it is a very small chip. It's a small chip. We are going to perform the operation on using the transistors. So in third generator, in 1950 to 60s, they used one or two transistors. In 60s to 70s, they are in a one ICs integrated chips. They started to design a multiple transistor inside that to perform multi-programming. Okay, multi-programming means parallelly running the program at a time. Okay, in fourth generation, from 1970s to 1990s, we used to microprocessors. Okay, so inside the microprocessors, we are having many registers, and very main heart of the microprocessor is arithmetic logic unit, where you will perform the basic operations. Every instruction is going to execute on that microprocessors. Okay, so example of microprocessor is leads to desktop computing. Okay, in 1971 they developed the first microprocessor, that is Intel 4004. In 1980s, they started the instruction set architecture, that is RISC and CISC. Okay, RISC means reduced instruction set architecture. CISC is complicated instruction set architectures. So next is fifth generation. From 1990s to nowadays, here we are started to using the parallel AI, artificial intelligence, and parallelisms. And so if you want to do some graphical or gaming process, we this is not that our CPU is not sufficient to do those things. So we move on to the multi-core CPUs, that is GPUs, that is graphical processing units. Those things and all developed after 2010. Next. So this the instruction set architecture, that is how your system is going to perform a particular instruction, because you are going to instruct a system as a high level language that will be converted into assembly level language using compilers. We will be having compiler, loader, linker in the system software, as these are all the system software in your operating system. So whatever program you are giving to it, that will be converting it into that is middle level language, that is assembly level language. How that assembly level language will be? It will be as a instructions, that is as a it will have operands, operators, and the code. Okay, either you have to load the memory, or you have to add them, or you are going to subtract, or you are going to divide. So these instructions will be there. Okay, after converting into a assembly level language, that will be converted into a machine level language, that is zeros and ones. Okay, so this instruction, how you are going to provide instructions, that is designed in the complex instruction set computer. Okay. What is complex instruction set computer is? It executes complex instructions that can perform multiple low-level operations such as memory access, arithmetic, and storage within a single instruction. Just we are going to give a single instructions. This instruction is going to separated into n type of small instructions. So that small instructions and all get executed one by one. Okay, in complex instruction computers. So it reduces the number of instructions required for a program, but increases the complexity of program because the we are going to provide as a single instructions that inside that single instructions that means, for example, add a comma b. If I give like that, so not it is not going to perform the addition of a and b directly. What it will do, it have to load the value of a inside the registers and b inside the register. We need a value of a and b. So for that you have to do the two load process, and then you are going to add that content, and then you are going to store it. Okay, so here itself we are having many memory access, that is from memory you are going to have it in the a and b. Okay, after accessing from memory, you are going to do arithmetic operations. After doing the arithmetic operation, you are going to store the result inside the some locations. Okay, so in and single instruction add A and B, it is going to have these three types of instructions, that is memory access, arithmetic, and storage. Okay, so we are having a number of that is number of instruction is reduced, but to process that instructions, we are having a complexity in this. Okay, so what is a key characteristic of CISC is complex instruction decode and variable length instructions. Okay, we will decode that complex instruction. So I said, right, is it possible to write here? Excuse me. Okay, so I can so this is a complex instruction, that is a comma add a comma b. So this complex instruction, it is divided into two things, that is load LDA R1, that is it is one of the register inside the processor R1 comma A. So the value of A will be load into the R1, and load R2 comma B, and then you will have the instruction here. Afterwards, you are going to store the instruction STA instruction, that is C, or accumulator. You know, if you store it in accumulator, that will be in the it is from accumulator. You are going to store it in some memory location, that is L1. Okay, assume it is a memory location. So a single instruction is going to decode into multiple operations. So these two operations are accessing the memory to register, and this is performing the arithmetic operation, and this is from register to memory. So these different type of operations is get decoded in a single instructions. And variable length instruction, just see here, here I am having two variables in my instructions. Likewise, in while storing it, you are having only one variable, that is STA. You are going to give this location LOC, okay, STA of LOC. Okay, so here I am having two variables, here I am having only one variable, so that is a variable length instruction will be there. Few general purpose registers as operations often involves memory directly. So we will be having R1, R2, R3, some general purpose of this accumulator will be there, or so in-depth, implied operations, that is arithmetic operations, can be get stored inside this accumulator. So multiple addressing modes will be there. So we will see later what is addressing modes. Addressing modes is different type of addressings will be there instructions may take multiple clock cycle to execute. Okay, what is clock cycle is, as in a single clock cycles you can execute n number of instructions. Okay, one complete clock cycles may used to execute a single instructions, but inside that you will have a multiple operations. Okay, so example of this is this Intel x86, IBM 370, VAX 11 and 780. So this is about complex instruction set computer. Next is reduced instruction set computer. So to overcome the drawbacks of complex instruction set computer, they have designed this reduced instruction set computers. Okay. It is a small set of simple instructions. So instructions to execute the operations is, that is a microprocessor should know, is limited one. Okay, here they have limited the number of instructions. Mm, so that the speed and efficiency will be more in the risk. And if you want to perform a complex task, we should use the software here. Okay, but in CISC, you don't want to use the software to perform the complex task, because we are having many instructions on CISC. Okay, compared to RISC. So the key characteristic of RISC is the fixed length instructions. Always, all the instructions will have only a fixed length. That is, only two operators will be there and one operand will be there, and simple decoding. The decoding will be very simple, and we are having more number of general purpose registers to perform for efficient operations. Okay, and simple addressing mode and few data types are there. So this is mainly useful for pipelining. Okay, that is parallel processing. This risk will be very useful. Okay, so we will study what is pipelining here. It is a very important topic for pipelining. Okay, the example of risk processor is ARM, MIPS, and Spark and PowerPCs. Okay. Now we will compare what is CISC and versus RISC. Okay. So instruction complexity. The CISC uses complex instructions. I already told CISC will have n number of instructions. Many instructions will be there. Okay, and it is used, the instruction itself perform that complex instructions. That, okay, complex methods. But CISC instructions, we will have only simple instruction. If I want to perform any complex instructions, I have to rely on software. That is, through software, I have to decode into simple one. Okay, and execution time. So RISC executes instruction in a single clock cycle, whereas CISC requires multiple cycles. I already told the CISC, it will divides the instructions into n number of sub instructions. Okay, so we need multiple cycles to execute those instructions. But in RISC, it will only one operation will be done on single clock cycles. That is, that whole instruction will be get executed on that single clock cycle itself. But in CISC, we need many cycles to perform that operations. And pipelining. So RISC supports pipelining. That is, pipelining means what is, sequence means what. So assume if I am going to execute the instructions, this instructions will be separate into 4 operations. One is fetch, another one is decode, another one is execute, and then write back. Okay, that assume you are going to run a program. Each program line will be converted into a single instructions. That instruction will be moved, that is, single instruction means assembly level language, that will convert into assembly level language. After converting into assembly level language, this will be processed, converted into machine level language, that will be processed inside the processor. Okay, while processing it, it will come across 4 different operation. One is fetch, Another one is decode. Another one is execute. Another one is write back. That is writing back to the memory. Fetch means if you are having any value that have to be fetched either from memory or from any register. Okay, from memory you are going to fetch the data, fetch the instructions. You are going to fetch the instructions and you are going to decode that instruction, and then you are going to execute this instruction, and then after getting any result you have to store it in memory back again, right? So this write back will do this operations. Okay, first it will get the instruction from the memory, decode that instruction into machine learnable form, and then it will execute that instruction. After executing, it will write back this to the memory. So assume this is a sequence of, this is how that instruction will execute under this 4 phase. Pipelining means while performing this fetching, or sorry, decoding, this fetching unit will be free. Okay, it will be free, it won't have any work. So what I can do, I can use it to fetch the next instruction. Okay, you can use this for next instruction. So that is possible in RISC. Okay, so in CISC, only at a time only one instruction is get processed. In RISC, you can process multiple instruction at a time. Okay, because if my first instruction is in the phase of decode, the fetch in the unit will be free. So I am going to use that for fetching the next instruction. Okay, next instruction. Sorry for scribbling like this. So if my first instructions moves to the execution phase, then the decode will be free. This next, the instruction that is fetched already can be moved to the decode instructions. Okay, so at a time I can process the parallelly I can process the 4 instructions at a time. That's why it is completing the execution in a single clock cycle itself. Okay, do you understand why it is using multiple clock cycle and it is using single clock cycle? CISC, we need 4 clock cycle to complete these 4 operations. But if in RISC, I am using a pipelining concept. So at a time, 4 instructions can be performed in a single clock cycle itself. Okay, and power consumption. So we all know the RISC consumes less power compared to CISC because single instructions need multiple cycle. So that means it may take more time to execute the instructions. That's why the power consumption will be more. The code size. CISC has a smaller code size while the RISC requires more memory for additional instructions. Okay. So here the instructions will be more. What is the application of RISC is high performance applications like telecommunications, video processing, and mobile devices applications can be is using the RISC, and CISC we will use in a normal desktops, low end home automations. There we will use this RISC. So now we will see what is the functional unit of computer. Okay. So these are the components of computer. We physically know what are the things available. Okay. We can view a monitor, we can view the keyboard, mouse, and then CPU, central processing unit. Inside the central processing unit, what are the parts we are having that we should know those things. Okay, what are the input units we know is how we are going to provide input to the systems. Okay, through mouse we will send give inputs. Then just see I am clicking here. So this is input providing to the system. Okay, and through keyboards, through microphones, I am speaking via microphones. So these are all inputs. I am giving the audio input to the systems. Okay, so this will be given to the main memory that will be sorry. Okay. So this is input unit. Output unit, you people know what is monitor, that is monitor, printer, speaker, everything is the output unit. And in CPU, we'll be having these three main information, that is control units, ALU, arithmetic logic units, and internal storage units. So ALU is the heart of the or brain of the computers. Okay. This is only going to execute every instructions you are providing to your computer, that is arithmetic and logic units. So it can do only the arithmetic operations and logical operations. I think you people know what is arithmetic operations, that is addition, subtraction, multiplications, divisions, these things and all arithmetic operation. And logical operation is compare, whether it is less than 0, whether it is greater than 0, or you are going to move it to the another location. So these things and all come under logic units. Okay. Control units will provide what type of signals I am going to send. Okay, that means what type of operation I am going to do, whether I'm going to fetch information from memory, or I'm going to send signal to the output unit, or I'm going to process, that is get data from input unit. So these things will be assumed by the control unit. Okay, and we will be having some internal memories such as registers and cache memory. These are all internal memories. What is the purpose of having internal memory is to process quickly. Okay, that is the process to reduce the processing time. We are having some internal memories, and main memory is used for instruction executions, and then secondary memory is used to store some programs or data permanently. Okay. This is the functional units of computer. Okay. So these are the in-depth. So first, the central processing unit. What is the operations? What are the operations it can do is, it will execute the instructions, it will perform calculations and handle those things efficiently. Okay, that is, it executes arithmetic and logic operations, and CPU controls data flow within the system using the control unit. Okay, the control unit will do this data flow operation and memory operations, these things and all done by the control unit, and arithmetic operations. So these things and all controlled by the control units. Okay. Okay. So from memory to I/O devices, communications can be done through the CPU units only. So CPU can perform use you can it can use the pipelining and superscalar executions. That is, these are all used for to speed up your or efficiently run your instructions. Okay, what is memory unit? You are going to store the programs and data. Just listen, your microprocessor or central processing unit will know only the instructions, that is mission level languages. So for that, we need to have the program and data. Okay, so the program will instruct the processor to execute what are the operations it is going to do, and data you are going to use on that operations. Okay, so the memory units where you will store the programs and data. Okay, so there are two types of memories, that is primary memory, secondary memory. The primary memory is, it's a main memory, you can call it as a main memory, where I will store the instructions, that is program, what it is going to execute now. Okay, if any power or it is a volatile, okay, volatile memory. It is the whatever whenever the power is get switched off, then the data will be get erased. So it is the data will be a temporary data. Okay. The example of main memory is RAM, that is random access memory, and ROM. Okay, read only memory. Okay, so in this read only memory, either we are having many types, that is erasable read only memory, programmable read only memory, static read only memory, those things and all there. So the and secondary memory is our hard disk. Hard disk drive is a secondary memory where the data will be stored permanently. Okay, if you delete this, then only it will get delete off, erase it off. Otherwise, the data will be stored in the secondary memory permanently. That is our hard disk and all come under secondary memory. So cache memory is the intermediate memory that will be present between the processor and then between the processor and main memory. Okay, so if you are having a processor here and main memory, your cache memory will be here. Okay. So whatever instruction executed early will be stored in the cache memory. Suppose if your processor is going to assume I'm going to print some welcome message n times. Okay. So this instruction is going to be execute n times, it is going to execute. Okay. So that same instruction going to fetch from the cache. Okay. So this, if that instruction is processed once, I don't want to go to main memory and take that instructions back to the processor. So because it is will take a time to complete fetch and store it in the processor. So you can fetch directly from the cache memory, the time will be get reduced. Okay, so whatever instruction processed earlier will be stored here. Okay, so if a new instruction arrives, if the capacity of the cache is full, what it will do is it will delete the what is the earlier most instructions. Okay, that is the cache memory. So it is intermediate memory to reduce the processing time. Instead of going to main memory, that is RAM, instead of going to RAM, it will, your processor is going to fetch that instruction from the cache memory itself. So this is the use of cache memory. So this is a hierarchy of memory we are having in your central processing unit. Okay, inside the processor, inside the microprocessor, I will be having a memory called register. Okay, I will be having the memory called registers. Here I can store one byte of information will be stored in the registers, and we are having two levels of cache memory, that is on chip L1 cache memory. So this will be present inside the microprocessor. Okay, so that is processor. Okay, so the register L1 cache will be present inside the microprocessor, and cache of chip L2 will be present inside the uh, outside the memory processor. And then we will be having main memory and then secondary memory. Okay, so these are the level 0, 1, 2, 3, 4, 5. Just see, from level 0 to level 5, the speed will be reduced. Okay, that is from level 5 to level 0, the speed will be faster. That is from processor to register, the time taken to access the values from the register will be very less. Then taking time from fetching from the secondary memory. Okay, it takes larger time, it takes smaller time. Okay, your processor will fetch information from the register very quickly, and here, from the secondary memory it takes some time. Okay, and here it is storage will be costlier in LO, and here it will be cheaper. Okay. The CPU registers holds the word retrieved from L1 cache. Okay, so the register will store the word from L1 or from register to cache also possible. So the L1 cache holds the cache line retrieved from the L2 cache memory, and the L2 cache holds cache line retrieved from main memory, and main memory holds the disk block retrieved from local memory. Listen, before execution, it is going to fetch the program. If you are going to run a program, just see, yeah, I am showing this PPT. So this PPT will be get running in my microprocessor, where I have stored this PPT. I have stored in my local, that is secondary memory. Okay, local disk, that is in a desktop or C colon or D colon. I will be storing this PPT. From that PPT, this will be get loaded into your main memory, that is RAM. I will be loading from that RAM. It is moved to the cache and then registers. To view this PPT, this is how your memory hierarchy will be useful flow. Okay. So this is about the memory unit, and so how we are separating this level of memory is by means of speed and capacity. The register can store only a 1 byte of information. Likewise, cache will have some secondary storage. You are having up to 1 TB like that. So RAM and all 256 RAM. Now we have 1 TB of RAM. Okay, now it is available for 1 TB of RAMs and all available. So if you move down, the capacity of storage will be more from register to secondary memory. Likewise, speed will be less from register to secondary memory compared to memory. So that's why here they have given that is registers are fastest but smallest, while the secondary memory is larger but slower, impacting data access efficiency. Now the next functional unit is input output systems. Okay, if I want to communicate between us to central system, that is microprocessor, how we can communicate is through a input unit and output unit. Okay, there are three types of peripherals, that is input peripheral, output peripheral, and input output peripheral. So input peripherals and a peripheral is the end level systems. Input peripheral is it will get the informations from the through keyboard, mouse, and all. Okay, output peripheral, the information will be shown to the X members, that is allow information from the computer to the outside worlds, that is printer, monitors, and all. Input output, that will act as both input and output, that is printer come with the scanner options. So that is one example, and the touch screens and all. One of the example of input output peripherals. This system have both the operations. It will send the input and then receive the output. Okay. If I want to communicate between the system and input output unit, we should have some interface, that is intermediate to communicate between the input and CPU, output and the CPU. Okay. For that, we are having a special component, that is input output interface unit we will be having. So through bus, we will communicate between the input unit and the processors. Likewise, from memory to the other processor, we will communicate via bus. Okay. Okay. So these are the modes of I/O data transfer. How we will transfer the informations from the input or output unit to the CPU. Okay, that we will see. So three modes, that is programmed I/O, and then interrupt initiated IO and direct memory access. This data is transferred between IO devices and memory. Okay, the programmed IO is used to send and receives data explicitly. So we are from CPU, from memory to input unit, you can directly access or through our CPU. Okay, likewise interrupted initiate IO. So it is not going to wait. Okay, you while it will initiate the IO operation but does not wait. It will start doing the other operations. Assume I am having the CPU and it is executing some instructions, and I'm going to touch on keyboard button here. So this is one interruption arise to your CPU. Okay, that is some signals you are going to provide, interruptions you are going to provide here. So it will send the instructions and it won't wait for CPU to come. Okay, so it will send the instruction even it is executing the instructions. So after completing these instructions, this will again process this new interruption work will be done. Okay, direct memory access. So you are going to have a special control in this memory CPU. That is, it is going to transfer the data between memory and IO devices directly without CPU. Okay. So in programmed IO and interrupt IO, we need a CPU to interact from IO devices to memory. But in direct memory access, you don't want to send signal to the CPU, central processing unit, to fetch information from memory or provide information to the memory. So you can directly access this using direct memory access. Okay. So next, the main heart of the functional unit is the arithmetic logic unit. In arithmetic logic unit, um, it is used to perform arithmetic operations and logical operations. This is the ALU, where A0, A1, A2 is the operand 1 signals. Okay. Here I am. So here I'm having a 4 byte of informations. Okay. So the value will be A can store 4 bytes of information, that is maximum up to 16. Correct? Yes, I think so. Because this is 2 power 0, this is 2 power 1, this is 2 power 2, and this is 2 power 3. 2 power 0 is 1, 2 power 2 is 2, and this is 4, and this is 8. Okay. So the maximum bit I can move is 15. Okay. So here I am having this is operand 1 and this is operand 2, because the addition and subtraction will have a 2 operands, right? If you want to perform addition, I need a operand 1 and operand 2. Operand 1 and operand 2. Okay. Operands are the value you are going to add, that is the operands. Operation is what operation you are going to perform, whether addition or subtraction. Okay, so these two are operands, value 1 and value 2, and this is a control signal. Okay, this is a control signal. So here you will have the control, just see LLL, that is what type of operation your arithmetic logic unit is going to perform. Okay, if everything is low, that is everything is 0, because your machine will understand only the zeros and ones. If everything is low, then it will perform complication of, that is a complication, complement of a it will perform. Okay, if it is 3, what is the 3 so sorry, the binary representation of 3 is 0 1 0 1. So it will take the complement of 3 and it will provide that as a output. Okay. Likewise, just see if 001 is there, it will perform addition of these two numbers and then take the complement. Okay. Here the one of the so it is taking complement A complement with and then adding with the B. Okay. Like this, each instruction, that is 16 type of operations I can perform, because I am having a 4 bits information. Okay, if it is a 4 bit, the total capacity I can have is 15. Okay, 16 type of informations from 00 to 111, 4 ones. So you'll be having 16 different type of instructions I can perform. Okay, so this is the arithmetic logic unit. So next is a control unit. So control unit is a component of computer central processing unit that directs the operations of the processor. Just see, I said no. These instructions will be come from the control unit. Okay, these instructions will be come from control unit. That is what type of operation it is going to do. Okay. Um, So the control signals will provide 3 types of signals, that is data signal, and then control signals, and then so this makes the processor steps through a series of micro operations in a proper sequence based on the program execution execute. So this is the functions of control unit. I already explained these 4 functions, that is fetching the instructions from the memory and decode the instructions to determine what need to be done. Okay, and if assume I am having C is equal to A plus B, this is my instructions to going to execute, then this will be decoded as add, assume this A value is stored in register 1 and B value is stored in register 2. So add R1 plus comma R2. Okay, this is the decode of this particular instruction. So you will be having a load and then store will be there, and control unit will generate control signals for each line of decoded instructions. Okay, what first I have to do? I have to get data from the memory and store it in the register. This is the first signal it will provide. The second signal is the data from the memory B and store it in the register R2. Okay, and then third signal it is going to give is adding these 2 things. Okay, and fourth signal it is going to give is storing it in the C. Okay, in the memory location C. Okay, and manage the data flow between the CPU and peripherals. Okay, that means from input unit, if you are going, if there is any input arise, that also managed by the control unit. Okay, so these are the functions the control unit will process. Okay, so these are there are 2 types of control units. One is hardwired control units and microprogrammed control units. It uses fixed logic circuits for fast execution, uses memory-based controls units. Okay, it is slightly slower. Okay, we saw what is arithmetic logic unit, we saw what is control unit, and we saw what is input output unit. These and all are separate units. Okay, I want to know how we are going to communicate between these units. We saw what are the operations the memory will do, processor will do, and output input will do. Okay, how these separate units are going to get communicate is via bus. Via bus. Okay, a group of line connected to a different device is called a bus. It used to carry a data and control signals. Okay, always you will get the data from the input unit and you will provide data to the output unit. From memory, you will provide, you are having a situation of getting data and program from the memory and to the memory. There is a possibility to store it inside the memory, and you are going to get it from the memory. And processor, what it will do is, it will process the operations whichever the control signals the processor. Okay, that's so single bus means only one bus will connect all the other inputs, all the other inputs. Okay, all the other units. And multiple bus, we will have multiple bus for multiple operations. Okay, for register operations, register files, you are using the bus A and B, that is input and output. Input, for input purpose, you will use the A and B. For output purpose, I am using the bus C. Okay, this is about bus structures. So the next is basic operation concepts. How you are going to perform, that is execute an instruction in a processor. Okay, we all know what are the functional units inside that microprocessor. That is ALU, control circuits, and several registers are there. So this is the architecture. That is main memory. We are having main memory, that is RAM, random access memory. Okay, once the execution is over and once the power is get off, then the whatever value stored inside the memory will get erased off. Okay, will get erased off. Okay, so this is our CPU. This is our CPU. This is our main memory. Okay, so these are the registers we are having inside our microprocessor. The one is, this is IO, that is instruction register. So if I am going to run a program, C program, assume you are going to run a C program. First instruction is int a equal to 5. Okay, C is equal to a plus 5. Assume these are the instructions I am giving inside a C program. So these instruction will be stored in the main memory as a program, and this will be loaded into your instruction register. That is, which instruction you are going to execute first will be stored in the instruction register. Okay, this is the program counter register. What is the purpose of program counter register is, it will have the next instruction address. Okay, that is, if this a equal to 5 is in the address 1001, so this 1001 will be stored in the program counter register. Okay, this is a memory address register. Okay, hold, so just see, int a is here. Okay, and as I am assigning a equal to 5, so this a is some memory location in your main memory. Is it so? Because I am assigning here, I am allocating a memory, and I am trying to store it in the value in a memory a equal to 5. Okay, so this address have to be present in your memory address register, then only I can store my 5 inside that location whenever the control signals ask to write it. Okay, so this is the process it will do. Okay, so in memory address unit register, it will store the address that particular instruction needed. Okay, memory data register, what it will do is, if suppose just see this instruction a equal to 5. Okay, this is, I am going to write the 5 inside the location a. Okay, so assume this location is here 1001. Okay, this control signals pass the read write signal. Okay, If it passes the right signal, what it will do? The data 5 will be stored in this memory data register that is going to store in the particular memory location. Okay, the control unit will send some signals such as read and write. Okay, read is used to read the value from the A and value from memory and store it in the memory data register. And if it provides signal write, what it will do? Whatever value in the memory data registers and whatever address provided in the memory address register, in that address this data will be get loaded. Okay, so this is the use of memory address register and memory data register. Memory address register holds the address of the memory location. Memory data register holds the read and write written to the memory. Okay, data that is going to read and write to the memory will be there. So these are the general purpose register. It will be useful to perform the arithmetic operations. Just listen. This A and 5 will be stored in these general purpose register to perform this arithmetic operations R0 and R1. So the A value, assume this is 5. This 5 will be stored in the R0 and again a 5 will be stored in R1. So these two will be added by the register arithmetic logic unit and store it back to the another register, that is R2. Okay, from R2 it will go load it into a memory data register, and this is control unit will provide the memory where I have to write. So this will be written in this main memory. Okay. So just see, we will see the what is program execution. To perform a task, a program consists of a list of instructions stored in memory. Individual instructions are fetched into the processor and executed. Okay, I told already what is that is initializing a value, and that is initializing the value. First, declaring the value int A is declaration, and assigning the value, and then performing the arithmetic operations. Okay. So these are the set list of instructions that will be stored in the memory. This individual instructions are fetched into the process. This, excuse me.
Yeah.
Excuse me.
From 3 minutes again. Yeah, we can continue on this again. Just what you mentioned. Thank you.
One minute, ma'am.
Yeah, it's okay. It's go ahead.
Is it a time up, ma'am?
Pardon, ma'am?
Hi, ma'am.
Pardon? Sorry?
Ma'am, shall I continue or?
Yes, yes, please go ahead. And for the duration of presentations, there are 3
It
minutes
is.
again.
Is it going to end? Okay,
Oh, yeah,
3 minutes
thank
then,
you.
right?
Yeah,
Oh, okay, okay, ma'am.
yeah, please go ahead. Thank you.
Did I want to continue this session or?
Yes, ma'am, please.
Okay.
Yeah.
I will complete with this instructions, execution of instruction, ma'am. Okay. Okay. So these are the points how it will execute, right? Program, that is, the program will be reside in memory, and program counter will initially have the first instruction memory. Okay, and this will gives to the memory address. So this will go and read the signals. That is, the your control unit will send the read signal. So it will read the particular instruction and store it into the memory address data register. Okay, so this will be sent back to the instruction register. Your ALU will perform operations on whatever present inside the instruction register, and then after performing it, this result will be stored back in the memory register, memory data register, and this memory address register will initiate write. Okay, this control signal will give a write operation. So the what where you are going to write the result will be present in this memory address register. See, these both will be get written inside this main memory. Okay, after completing that particular instructions, your PC will be incremented to next instructions. Okay, so while executing the instruction, you will get the interrupt and service routines. Okay, shall I? There are many points are there, that is performance measures, and or what is the trending things going on. That is, we are moving to the quantum computer. So how the quantum architecture will be there, how the efficiency will be there, how we are going to overcome the drawbacks arising in the, that is noise problem is arising in the quantum computing. So how we are going to develop the quantum architecture. This is the latest research going on. And then next is neuromorphic. So these are the new lines in the computer architectures. Mm. Ma'am? Ma'am? Hello? Hello? Processor speed and system scalability. In multi-core and it is designed for the system scalability and improve the processor speed when you perform the parallel operations. Should future computer architecture address the bottleneck cost? Future. So now the future is moving to the quantum computing. So they are designing the computer architect. This is in the on the way process of it's very new way of having a memory. You know, it's the memory itself. You are not going to store it as a bits. Okay, it will be in a quantum that is quantum form. So the future is it will be in a different way. Shall I? Whom I have completed. Hello. Hello, ma'am. I have completed, ma'am. Is there any other questions, or shall I quit? Hello. Hello. Ma'am, I can't understand. Can you type in chat what you are trying to say?
Hello, ma'am.
What are the trade-offs between processor speed and system scalability in multi-core and distributed architecture? Oh, we are having many.
Hello, ma'am.
I'm here only, Mama.
You can hear my.
Okay, okay.
Hello.
I mean, to increase the speed of the multi-core and distributed architecture, we are in distributed architecture. We will be having these systems. Systems can be run at different locations, right? The scalability of that distributed architecture will be more because whenever the system fails, you can add it properly, and you can use it there. And
Hello.
hello, ma'am. Okay, ma'am. That's all.
Oh, yeah. Okay. I guess someone else has spoken in. Yeah. Thank you for answer. Before I close this one, but please open your camera. I will take a picture on the computer. Okay, 1, 2, 3. Okay, another one. Thank you for your information. Finally, we come to the end of the picture today. Thank you for Ms. Shalini for the wonderful information and sharing your knowledge. We hope this information will be beneficial for all participants. At least we look forward to collaboration in the future. The physics lecture for today and the season. Thank you. And please stay. Thank you so much, ma'am.
Thank you, ma'am. Thank you so much for giving this opportunity. Thank you.